Okay, so y equals x to the third looks something like this. Y equals 27, that's just a horizontal line at 27 on the y-axis. And then they want us to rotate it around the y-axis. They say y equals 0 is another bounding region. I'm just not sure why they're telling us y equals 0. Because this y equals x to the third already crosses at the origin. But either way, I'm pretty sure this is the region they're looking for. I'll double check when I check my answer at the end. But they want to rotate this region around the y-axis. What we want to do is come up with the equation for an infinitely small right cylinder right here where I just drew. So take that off to the side. Imagine that it's not necessarily infinitely small so that we can actually visualize it. This is what the right cylinder is going to look like when it's rotated all the way around. So the distance from here to here is this distance. It's a radius. And the height is going to be infinitely small, so we're probably going to call that dy. So from here to here, that radius, that x distance, is determined by where we are on the y-axis. So you can rewrite this equation in terms of y, because dy looks like we're going to be taking the integral with respect to y. This is the infinitely small piece is measured in y coordinates. So we're going to be finding an integral with respect to y. So if you want to put this in terms of y, x is going to be the cubed root of y. And yeah, that's all we need to say there. X is the cubed root of y. Okay, so the volume for this infinitely small thing, sorry, that's my messages. The volume is the radius squared, so it's pi r squared. The radius, we said, is this from here to here. So it's the cubed root of y squared. And then it's dy because it's an infinitely small right cylinder. And then we want to integrate that on the y-axis, starting at 0 on the y to 27 on the y. So it's pi r squared, then h. So if you rewrite that integral a little bit before finding the antiderivative, the cubed root of y means y to the 1/3 power, so this is pi times y to the 2/3 power. And then when you find the antiderivative, the power is going to go up by 1, so it's going to have a 5/3 power. So we want to put a 3/5 in front of it. That way, when you take a derivative of this term, derivative of this turns back into this. Now all that's left is plugging in the limits of integration. Plug in 0 is no problem. Plug in 27. I'm not going to try to think about that algebraically. We probably could. Actually, that's probably quicker. Look, 27 to the 5/3 power. You could plug that in as 27 to the 1.666 power in your calculator, but that's the same thing as 27 to the second over the cubed root of 27, so 27 to the 1/3, because powers on top, two numbers with the same base, the powers will subtract when they're being divided. This is like 6/3 subtracted by 1/3 makes 5/3, so this is the same thing. The calculator is faster because I still got to do 27 squared, and I'm going to divide that by the cubed root of 27, that's 243. So 27 to the 5/3 power, 243. And then if we multiply those, 729 pi over 5. Yeah, so I checked my answer. So this, what we just did is this rotated around the y-axis, but what they actually wanted was this area rotated around the y-axis. So what you can do to quickly get the final answer is you can say, well, take a right cylinder that goes all the way across. So this right cylinder has a height of 27, because that's the y coordinate. And then the distance across we already found was 3. Actually, no, we didn't do that in this video. Look, the x coordinate is 3, because if you were to plug in 27 into this equation to find out where they cross, you get x equals 3. So this thing has a radius of 3, so pi r squared times h. That's the volume of the whole right cylinder. And if you subtract out the volume that we just found, what was it? It was down here for an answer, we got 729 pi over 5. So if we do 3 times 3 times 27, and then to get that with common denominators, I'm going to multiply that by 5, subtract the 729. I got 486 pi over 5.